Well, I hope you had a nice lunch. I can start?
Yeah, pleasure to have Anton speaking to us about stochastic modeling.
So my name is Anton Camacho. I'm a lecturer at the London School of Hygiene and Tropical Medicine. And that's a talk that is based on the introduction of my thesis. So I just try to recap like the basics of stochastic modeling. And I will also, I mean, the plan is to recall some basic concepts of mathematical modeling. And usually it's easier to start with deterministic and then move to stochastics. But actually, if you look at how all these things are derived, initially everything is stochastic, and then you can derive some approximation that leads to some deterministic models. But it's usually easier to start with deterministic. So I will recall some basic concepts of infectious disease modeling. Then I will formally define the structure of stochastic models. And okay. Is that better? Okay. So this formalism will enable us to understand the relationship between deterministic models and stochastic models. And then I will show several examples of application of stochastic models. So that means things that you cannot do with deterministic models. And if I have time, I will do a bit of drawing. And I have everything, so that's fine. OK, so let's start with the kind of model we are considering. They are applied to some specific diseases that we call directly transmitted microparasitic infectious diseases. So it's what we show you later is compartmental models. And so why infectious disease? Because they can be passed between individuals. And so that's in contrary to other like non-transmissible disease, like for instance, many cancers that develop over an individual lifespan. And then when you consider the pathogen, you have either microparasitic or macroparasitic macroparasite, sorry. And the advantage of microparasite is that they develop quite quickly within the body, so you can neglect the within-host dynamic. So usually, our models doesn't include any within-host dynamic. And finally, whether it is a micro or the macroparasitic parasite, usually you can have like either direct or indirect transmission. And here, because we're going to use some mass action assumptions, we're going to consider just what we call directly transmitted microparasitic infectious diseases. So we can summarize usually what a model does by looking at the history of infection within an individual, and that will help us to describe what a model does. So usually you become infected at this time, and then initially you have a viral load that starts to increase slowly. During this time, you're not infectious. What we call you are exposed or latent. So before that, you were susceptible. Then at some point, you have like a viral load that becomes high enough, so you become infectious. But this viral load, as it increases, it also triggers an immune response in blue. And this immune response is going to repress the viral load. So you're going to end your infectious period, and you're going to recover. And then, as you recover, usually you are immune over the rest of your life, for instance, in the simple cases. So that's really the infectious status we are considering. We are actually not considering the medical status that may actually overlap with infectious status. For instance, you might be infectious before actually having the symptoms. And so that's really what we are interested in these three different stages. And that's what we describe as a SCIR model here for susceptible exposed infectious recover with some rate from one compartment to another that we're going to see in more details. So here Lambda is going to be the rate at which two individuals come into contact. So that's when I multiply by the number of infectious individuals, that's the per capita force of infection. And epsilon and nu are the inverse of the average latent period and infectious period. So that's really that basic thing you know already. And then you can, here I consider a much simpler model. This is the first model, first compartmental model that was proposed by Camacho and McKendrick in 1927. It's a SIR model, and you know these equations perfectly. We consider a fixed population size here. I'm going to call it omega in the rest of my talk for the population size. And this gives you this kind of dynamic with here the number of people infected over time that create this epidemic. The two important results of these very simple models, and they were quite remarkable at the time, is that an epidemic will occur only if the initial number of susceptible individuals is greater than a given threshold, and you recognize something that is equal to 1 over R0 times the population size. And at the end of the epidemic, the second result is that it will remain some people that won't be infected. So not everyone will be infected during the epidemic. And you have some implicit, so S infinite, which is the number of people remaining susceptible in the population at the end of the epidemic, is the solution of this implicit equation. So usually you solve this numerically. And so yeah, so that was the two main results of Camacho and McKendrick. And actually, well, because of the nonlinearity in these models, it's quite difficult to get a lot of analytical results, usually for compartmental model. But one thing that you might want to do is to also switch the formalisms and go to stochastic models. So these are three reasons why you might want to consider stochastic models. The first one is that the way epidemic propagate is inherently stochastic. You might think that when you meet someone that is infected, you have a certain probability that it will pass you the pathogen, and it's not a yes or no, you have some chance here. Some phenomena are stochastic by nature and cannot be described in a deterministic setting. So think about like stochastic extinction, when you have a few people infected in a population, and just by chance they will recover before passing on the disease. So just by chance, the chain of transmission will stop, and you have what we call a stochastic extinction. And finally, when we study epidemics, we are interested in the variability of the different outcomes that may happen. And this variability usually is due to stochasticity. And this is especially important when you want to do forecasting. When you want to do a forecast, you're not interested only on having a point estimate, but a range of possibility. And that usually is given as a probabilistic distribution. And so that's why you might want to consider also stochastic models. So there are three categories of stochastic sources in a model. The first one is demographic stochasticity, which is also called internal stochasticity. And that really arises at the individual level, the fact that individuals, chance events at the individual levels, this is gonna lead to demographic stochasticity at the population level, so the variability at the individual level. So that's called internal. The second one is external. It's also called environmental stochasticity. So, for instance, yesterday we had the monsoon, so that's a kind of unexpected, and that can have like a huge impact on the, well, depending on the disease, cholera, for instance. So that's the external forcing that may depend on all the stochasticity in the environment that may force your system, also the transmission. And finally, there is observational stochasticity, which is also some kind of like external, but it's a bit special. It's just the way we observe epidemics. the way we observe the number of cases. This is something that comes with some error, and so we might want to try to quantify it. I mean, try to put some probabilistic description on this. So I'm going to go on these three sources of stochasticity on the other way, because it's more simple than this. So let's consider the observation stochasticity. So that comes the fact that, for instance, when you do a diagnostic, this comes with some errors. There is some false positive, some false negative. Plus, there is also some incomplete reporting. So we know, for instance, that we don't observe all the measles cases, despite the fact that measles is quite easy to diagnose. We don't observe all the cases. So we might want to consider underreporting, for instance, if you want to model measles. And also the reporting rate, so for instance 60%, that might change over time depending on how your surveillance system behaves, if it's closed on the weekend, for instance, or if at a certain point of the year is more active than other. So all these things might change over time, and you might want to model this, for instance, with by saying that if your reporting rate, so that the proportion of cases that you report in the data at time t is taken from a gamma distribution, for instance. So rho t is the reporting rate. And if conditional on the reporting rate, you model the reporting of cases as a Poisson distribution, then if you mix these two things, if you convolute, you obtain a negative binomial distribution, which means that you have this, you model the underreporting here, and you have some over dispersion you have some over dispersion of the reporting. So that's something that is quite commonly used, and so you can here have some mechanistic description of why we use this negative binomial observation, and that's quite commonly used. But there are other sources. I mean, there are other ways to quantify the stochastic observation. Then let's have a look at the environmental stochasticity. So you can do that, for instance, by just taking a deterministic model and just adding some environmental stochasticity. So that's just what I did in the SIR model. I multiplied the contact rate by a factor that is partially stochastic. Like I can say that this variable is random, and so all the system become also stochastic. And here you see that I really force the force of the mass action with this environmental random noise, and that's how you can model also this kind of sources. So that's really quite simple to do. So for instance, you can take something that is Gaussian here, for instance. And finally, the demographic stochasticity is the one that is going to be quite interesting here, because it results from the fact that my population is made of discrete entities, individuals, and so I'm gonna have to change my formalisms. So now my state space is going to be a vector of integers. SIR, and the idea is that I'm going to model the individual events. And so, for instance, I'm going to say that the infectious period, well, it's come from a distribution which has some mean and some variance, and that the number of contacts between individuals, well, it's between, given like I have an infective individual, it's going to contact a given other individuals according to a Poisson process with intensity beta over omega. So now I introduce the beta, which is the per capita contact rate. And usually with only these two assumptions, the only thing you can do is to compute the distribution of the final size of the epidemic. So the distribution of the number of cases that will be infected during the SIR epidemic. That's usually what only thing you can do, and you can find some results here. But if you want to go further, you need to get some Markov property. So you need to make the infectious period the lack of memory property of the infectious period thanks to an exponential distribution. So if you assume that the infectious period is exponentially distributed, then you have the memory property, and then this becomes a discrete state continuous time Markov process. And then in this case, you're going to be able to say more things. So the way we describe it is not, well, in terms of a differential equation, obviously, but usually we write a table with describing the transition. So an infection is when I put one guy in the susceptible compartment and I put in the infectious. So my new state of the population is going to look like this. Recovery, and tells me that the probability within a given time interval is proportional to the rate times this time interval. So, so that's the Bartlett model. So it's the stochastic version of the Kerr-Mackendrick model. And you can see that we had to wait 20 years before this was defined properly. So the model we are going to talk about, the stochastic models, actually they generalize the Bartlett model to any kind of model you want, compartmental model you want. And their name is density-dependent jump Markov processes. And so that's the not so nice part, but I had to put it anyway. Is that you can define this in a way very general. So let's say you have D compartments and M transitions, whatever you want. You're gonna define the vector of the states X, so that is length dimension D. So that's the vector of the state of the population at time T. And for each transition, T index M, with M varying from M1 to capital M, the number of all the transitions. So in the SIR model, you have 3 states, 2 transitions, but you can have many more transitions. So we're going to define a vector of state change. So for each transition, we define a vector of length, the dimension of the state space. That's going to tell me if I'm going to add or remove people in this compartment. So that's really like this. That's the transitions. And a jump intensity that generalizes also what we saw before. So this jump intensity tells me that the probability to jump is proportional to the time interval I consider. And that's the complementary, so the probability to stay on the same states of the system is 1 minus the probability to jump somewhere else. So that's why we call it a jump Markov process. And this process is density dependent only if we can rewrite the jump intensities as something that is proportional to the population size. So omega is the number of individuals in my population, and here I assume that it's constant. So most of the time, all the model you will write actually are like this. If you look at all the transitions, there is something multiplied by a compartment, and a compartment scale can be scaled in terms of the population size. So yeah, almost all Markov models used in epidemiology are density-dependent jump Markov processes. That's the natural formalism to model demographic stochasticity. And again, it has some very limited analytical results. It's only on the final size of the outbreak that you can derive some results. But then you can do many more things like approximation, diffusion approximation, and you can have like much more results on this. The other thing is that you're going to be, you can simulate this also. I will show you later. So the problem is that the law of xt, the stochastic process at every time t, is not tractable. And this is because of the nonlinearity in the contact process. If you remove the nonlinearity in the mass action assumption, then you can have some results. But here it's not possible. So to study the dynamic of this model, this stochastic model, you have two solutions. Either you do some Monte Carlo approach, meaning you're going to simulate a lot your stochastic model, and then you're going to use a Monte Carlo approximation to evaluate the law of xt at some time. Or you can do analytical approximations. That's going to, the idea is to derive some equations easy to solve for the first few moments of xt. So xt is really the distribution of my state space at time t. But this will be only valid when the population is large. So let's have a look first at the Monte Carlo approach. That's what we call usually the Gillespie algorithm, or actually Gillespie is a chemical physician. And Du was a mathematician who wrote the algorithm, and Gillespie simulated it. So not like the big difference, like almost 30 years between the moment where the algorithm was written and when it became popular. So given, the idea is that given a state x and a time t, I want to simulate the following event. I don't want any transition to occur during the time interval between t and t plus tau. And then at time tau, t plus tau, sorry, the transition tau mu occurs. And actually, you can see that, so tau, the time, and mu, the index of the transitions, these are two random variables with the following probability density. So here you recognize an exponential probability density. And this is just a uniform. So the idea is that you have different exponential clock, one for each transition, and you're going to look the time at which the first one is going to ring. That's going to be this variable. And then you're going to pick the transition by looking at proportional to the intensity of this transition, comparing to the other. So A0 is just the sum of all the intensity. The thing is that for large population, if you look at the expectation of tau, like the time you're going to advance the algorithm, is proportional to 1 over the sum of the jump in density. And because we have a density dependent process, this scales in terms of the population size. So you have something that scales in 1 over the population size for the expected time you're going to advance the algorithm. Which means that as the population gets larger and larger, if you consider 1 million individuals, you see that you're going to do very small steps. And that's why it's going to take very long to simulate your model. So usually you want to use this algorithm only when you have a small population size. Otherwise, you're going to run simulations for days or weeks. The thing is that as the population gets larger, you may expect that the stochastic effects will be weaker. So it might be more interesting to use what we call an approximation. And analytical approximations, they were also defined in the 70s by Thomas Kurtz. And the first result is a large population limit of the stochastic process. So as the population tends to infinity, what you can see is that you can derive a deterministic system where a deterministic system that actually corresponds to the deterministic model. So this is like a general form. This f function depends on the jump intensity, but also remind that when you look at the deterministic and stochastic SIR model, the rates of the deterministic model are very similar to the jump intensities of the stochastic model. So this is what you retrieve here. And that's why the Kermack and McKendrick SIR model can be retrieved as a large population limit of Bartlett's SIR model. So that's usually something that we can do like manually. You look at the model and you derive the deterministic equations, but this is the formal proof that it works. Well, this isn't the proof, but that's the results of the proof. And the second step is to study not only the large population limit, but also the deviation from this large population limit. And the deviation of, so that's the rescale, when you rescale the process from the deterministic solution. So that's the x divided by the population size. How much it deviates from the deterministic solution. And that's a central limit theorem that establishes that this deviation are Gaussian and of the order of 1 over the square root of omega. So that's a very typical result of central limit theorem, like everything scale as the square root of the sample size, if you want, or here the population size. So actually, following these two theorems, you can approximate in distribution the stochastic process X by the sum of two processes, one deterministic and one stochastic, with the right scaling factor. And what you can know, you are interested in this solution and this stochastic process. And actually, because this is Gaussian and this is the solution of the deterministic system, well, you can also write some equation for the variance, for instance, of this process. And the idea is that with a few deterministic equations, you can write how this Gaussian process is going to evolve. So the idea is that you don't have to simulate anymore the stochastic process. You simulate a few set of equations that drive the mean and the variance of your Gaussian process, the Gaussian approximation. So just to show you like graphically what all this means. So let's say that I had done a lot of Monte Carlo simulations to simulate a SIR model. So I'm just considering the number of infectious over time. So you recognize the bell-shaped epidemic. And you see that every time I have some variability. So when it's red, that means I have a bigger probability mass here. And so you can see in the color is the Monte Carlo simulations, and the black line and so the black solid and dashed lines, they correspond to the Gaussian approximation, and that's just the 95% quantile of the Gaussian approximation. And so this takes half a second to simulate, whereas this takes usually like several minutes. And you see that you have a good approximation here of the stochastic process. This is when I start with the large initial conditions. This is one of the assumption of the Gaussian approximation is that you are always far from 0 here. And that's why I start quite far here. If I start with a small initial condition, something that is not the order of the population size, you see that initially I have some risk of extinction. I have some mass that goes to 0 quite quickly. And otherwise, I have an epidemic. But now if I look at my second order approximation, so the variance of the Gaussian approximation, I have these big bumps that show here, and that are not realistic. And that's just because I'm not in agreement with the assumption. So it's the kind of approximation you need to be careful when you use it, obviously. And so sometimes you see in the articles they just cut here and they just interpret this as being 2 bumps possible, but that's not the case, obviously. So that was just like for the bit of the theoretical results, and just to show you the link between deterministic and stochastic, and the fact that they are complementary. It's not either one or the other. They have some benefit, like speed for deterministic versus precision for stochastic. And you need to be able to use this kind of approach. And usually this is quite easy because they are the same description at the very low level. Is the individual base description. So now I'm going to look at 4 contributions of stochastic modeling to epidemiology. The first one is the initial risk of extinction. So we saw that in the deterministic SIR model. Yes? Sorry?
What guarantees that f, I, and r are always greater than or equal to 0? In the stochastic case, in general, as you formulate it with the Gaussian?
Yes.
Is it guaranteed that they are greater than or equal to 0?
Well, the thing is that so this is not a diffusion approximation, it's the Gaussian approximation. So the mean is driven by the deterministic solution. So usually this is positive, but the variance, you can have all sorts of degeneracy that leads to you can have negative solutions. So it's uncoupled. So the variance depend on the mean, but the mean doesn't depend on the variance. So usually, if the deterministic solution stay positive, you won't have any problem in deriving the Gaussian approximation for the mean. But the variance, you can have all sorts of crazy things. If at some point you get too close to the boundaries of your positive domain, but there is no much like results. It's numerical analysis that tell you that.
With Monte Carlo, you'll never get a number that's less than 0. But with
if you do
analytic approximation, then you can get the.
Well, you will get this kind of. So with the Gillespie algorithm, no, you will never get well, unless you specify such a way that you want to deal with not anymore populations, but things that live on the could be negative also. But for epidemic modeling, if you define the thing properly, normally you don't have the problem of negative populations. Here the thing is that I just obtain the variance of my Gaussian at time t, and then because once I have the mean and the variance, I can look at the distribution. Sometimes my distribution span, well, it's defined on R, so it can go negative. But I never simulate trajectories here. I never look at individual trajectories. That makes sense? Okay. So the initial risk of extinction. We saw before that when you have a deterministic model, the first thing you want is to look at the reproduction number, the basic reproduction number. And usually you derive this as a function of the parameter of your model. And you know that you have an epidemic if R0 is greater than 1. Actually, in a stochastic model, even when R0 is greater than 1, you might not necessarily have a major epidemic. The idea is that the initial phase of the epidemic can be described by a burst death process. So imagine that you have a population, big population, with a lot of susceptible individuals, and you just introduce one infectious individual. Well, this guy, so you have one infectious individual, and he stays infectious for some random duration, and he's going to infect some other people at different time, according to the Poisson process. So for instance, this guy and this guy. So if you look at the time series, so here you have only one person infected. Here you have a second one. Here you have a third one. Then here, this guy recover. This guy recover. And this guy recover. So that's the initial phase where you have this guy who infect two people. And then these two ones, they can also infect other people. And that means that in the initial stage, we don't really look at how many susceptibles there are. There are so many susceptibles that you consider that you have an infinite number of susceptibles. And so maybe these guys are going to infect also some other people. Maybe this one is just going to infect another one. And so what might happen is that maybe this one will not infect anyone. after some point, you might see that when you look at the epidemic curve, it goes up, some exponential increase. And that's because, like, for instance, well, everyone passes on the disease. You have a R0 that is above than 1. But it might happen also that these guys, just by chance, they recover before passing on the pathogen. And so what you're going to see, actually, is also something that's going to increase. But then at some point, it's going to die out before giving rise to a big epidemic. So that's what we call the initial risk of extinction. And you can see that the bigger is R0, the less likely this is to happen because this guy will pass the pathogen to more people. The idea is, can we quantify this? And the answer is yes. We can have some results. And these results come from birth-death processes. So when you remove the assumption of susceptible depletion, you simplify your SIR model to something that is just a birth-death process, a branching process. This is my branching process. At every generation, I create new infected people. So for epidemic, birth means infecting, and death means recovering. And because we have the law of the how long you stay infectious and the law of how you contact people, then you can have some analytical results. So the idea is that the probability Px, the probability of extinction, so the probability of the birth-death process stops after a finite number of generations. So that's this case. If it doesn't stop after a finite number of generations, you are in this case. And at this time, the approximation won't be valid anymore because you have to consider susceptible depletion. But we are interested in this case. So when you stop this process in a finite number of generations, this probability is equal to Q to the power I0. So Q is something that we want to determine, and I0 is the initial number of infectious people. You see, because here I have only one guy at the beginning, so it's 1, for instance. But I could have said that I start, for instance, with 2 people infectious. And because I have infinite amount of susceptible people, these 2 are independent. So that's why if my probability is Q for one guy, well, it's going to be Q to the power I0 for I0 guys, because they are all independent. That's the good thing with assuming that the population of susceptible is infinite at the beginning. And then you can show that Q is the unique root between 0 and 1 of the equation S equal F of S. With F of S, you can this is you can recognize some kind of probability generation function so that's the Poisson process, and that's the distribution of the infectious period. So here, this is the Poisson process, and this is what you recognize the probability density function of the infectious period. And here again, because we are in the formalisms of density jump Markov process, we have very limited choice for this, but still we have some choice, is that we can set this PDF to be any gamma distribution where the shape is equal to an integer. So what does that mean? It means that we can, for the duration of the infectious period, we don't necessarily want to assume an exponential distribution. We can have a more general family of functions that is called Erlang distribution. And the idea is that if instead of having one I compartment, I model k different I compartment, I1 to Ik, and that the rate at which I exit any of these compartments is equal to k times nu, which is the inverse of the average infectious period, then I can obtain this kind of distribution. So that's when k equal to 1, Here, this is the exponential distribution. But as k increase, the distribution becomes bell-shaped, looks more like a Gaussian, and eventually goes to a Dirac. So that's a very flexible family that gives you a wide range of distribution, and usually it's biologically much more realistic. Usually people use exponential because it's mathematically convenient, but actually you can use any of the Erlang distribution you want. So that's the probability density function. And when you look at the variance, you can see that it's 1. So it's equal to the variance of the exponential distribution divided by k. So the more the subcompartment you have, the less variability you have in your infectious period. So I think I have time to quickly look at the. So how can we derive the probability px? So I'm interested in the solution S equal f of s being the integral between 0 and plus infinity of exponential beta t 1 minus s. And now I'm replacing gi by my probability density function of the Erlang distribution. K minus 1 exponential minus k mu t ds. And this is over factorial k minus 1. So you need to integrate this. And so actually it's not that tricky. You just remove everything outside that doesn't depend on, so it's not ds, it's dt here. S, you just want it to be below 1. And so if you remove this, you see some pattern that arise is that exponential. So you can group the t here, exponential minus t beta 1 minus s plus k mu times t k minus 1 dt. And so to integrate this, well, unless you know exactly the solution, you can do that by part. So you define this to be u and this to be v prime. So usually you see that because it's so when you integrate v prime u, it's equal to uv minus v u prime. And so then you need to compute all these things, but the v. So I'm gonna put this equal to a notation, and you see that this is always positive. So v, this is v prime. V is equal to one over minus a exponential minus ta. And u prime, and u prime, is equal to k minus 1 t k minus 2. So when you look at v times u, you see that actually between 0 and plus infinity, this is going to be 0. So this is always going to be equal to 0. And so now you're interested in this times this. So what you're going to retrieve here, it's k mu over k minus 1 factorial integrate between infinity of 1t a t k minus 2 dt, and the constant term that are going to exit are actually the k minus 1 and the minus a times minus is going to be plus. So you have something that is very similar, but you see that the factorial here is going to become k minus 2. And if you do that again and again, k minus 1 times, what you obtain at the end is just, so that's take k minus over k. And what you have on the bottom, because you're going to make this exit k minus 1 time, this is going to cancel the factorial here, and here you're going to obtain r to the power k also. And so the final expression for f de s is equal to k mu beta 1 minus s plus k mu to the power k. Okay. So now the idea is to look at the simple case where k is equal to 1. So when k is equal to 1, I have an exponential distribution. So when k is equal to 1, I have one exponential distribution. So the solution I'm looking at is S equal to mu beta 1 minus S plus mu. And if you divide by mu both sides, is equal to R naught 1 minus S plus 1. And so this is a polynomial equation of degree 2, but there's two simple solutions. The first one is S equal to 1. And the second solution is S equal to 1 over R naught. And because I'm considering solution, I'm considering the root, the solution, so that it's between 0 and 1 excluded. So that's my Q, 1 over R naught. So in the simple exponential distribution, the extinction probability is equal at 1 over R naught to the power I0. So that means that you see that if you have a R naught that is very close to 1, you have a big chance of initial extinctions. And that's why, like, sometimes, there's some disease, even if they're introduced in the human population, if the R naught is close to 1, you might need to have multiple introduction before a big epidemic starts. And that's a result of stochastic processes. Obviously, if I consider a k greater than 1, I need to deal with a polynomial equation of greater order. And so for k equal 2, I can look and obtain this expression for q. And actually, I can see easily that q is lower than q2 is lower than q1. So that means the probability. So that's and actually, for k greater than 3, I need to use numerical solutions. And this is the plot of the extinction probability, color-coded, as a function of R naught and the shape of the Erlang distribution. So here I use the same average infectious period. I just change the shape of the Erlang distribution. So as I go up, my infectious period, the variance decrease. And as I go there, my disease is more and more contagious. And so you see that here the probability decrease. There is more blue above than here. And that means that pathogens that have more variable infectious period actually have greater chance of getting extinct initially. So usually when you use an exponential distribution, you kind of overestimate the variability of the infectious period. That means that you're going to be a bit optimistic in the chance of the pathogen to go extinct quickly. Well, there was some consideration. I'm very happy I could write on the board in the mathematical institute for the first time in my life. So now I can say I need a bit of math. The second application is to look at critical community size. So what is a critical community size? It's the minimum size of a population that we assume it's closed, it has no contact with outside. So it's the minimum size of this population such that the pathogen can persist indefinitely. That sounds like a very mathematical definition. But what we can see already is that the value of the CCS will depend on the pathogen. For some pathogen, so the size of population is going to depend on the property of the pathogen. And so, for instance, we know that for measles, so I'm going to take measles as an example, this population size should be between 100,000 and 200,000 individuals. And that's come from empirical data. So that's, I think it's Bartlett who did that. What he did is that he looked at different cities, so every point is a different city. Yes? So,
what about the other sources of stochasticity?
So here is much more general the definition of critical community size. Is as I say, like what is the minimum population size such that my pathogen will always have enough susceptible to keep on transmitting without getting extinct. They probably have many factors that get into account for that, but one big component is going to be the stochastic effect at the individual level. But you could imagine that, for instance, like seasonal forcing, yeah, I guess like depending also on the kind of connection of the population, whether it's highly connected or not very connected, this is going to also play a big role in the critical community size. Obviously, here I'm going to simplify a lot the problem just to answer this question just by looking at the demographic stochasticity and not the other potential source of that can influence this CCS. But so that's empirical data in England. Each point is a city of England, and for each point I have in the x-axis the size of the city, and so for instance. Here I have a city with very few individuals, very small city. And I'm going to look at the mean annual duration of fade-outs. So what is the average duration where there is no case of measles reported in the city? So here you see that there are some epidemics in the city and some time period where there is nothing. So here it takes 16 weeks, I think, or yeah, I guess 16 weeks. Between two or 16 years between two epidemics. I think it's 16 months probably because this is years. So it's a number of months. And you see that as the population increase, well, the pattern of recurrent epidemic become more regular. So the entire epidemic period decrease. And so I obtain this curve with here, I guess it's London, where you have epidemics every year. Sorry. So how you define the CCS? Well, you look at the generation time of measles, which is around 3 weeks. So you know that if you have two cases that are separated by more than 3 weeks, that probably means that it's a reintroduction rather than a continuous transmission in the population. So you can define a threshold here as 3 weeks and look in the x-axis, what is the population size corresponding to this threshold? And you see that it's between 100,000 and 200,000, closer to 100,000. But how you can determine empirically the CCS. The problem is that this kind of data for measles, we don't have it for other diseases. And that's really important because if you know there is an area where potentially the population size is above the CCS, then you might want to use, for instance, vaccine or special interventions to treat this population. So you want to know what is the CCS. So there is a lack of such data for other diseases. So the idea is that can we estimate the CCS for any disease? And one solution is to use the stochastic modeling because the CCS cannot be linked to the concept of risk of extinction. And we saw that it's only with a stochastic framework that you can study the risk of extinction. So I'm going to use a simple model and try to validate it on measles. So here I have a SEIRS model. Well, not, sorry, it's a SEIR model with some deaths and births. So I'm going to fix the average life expectancy to 1 over mu. And so mu is the death rate. Here, you die when after recovering or during the infectious period. And you immediately enter in the susceptible compartment so that the population size remains constant. And so here it's very simple, and there is no along distribution, it's everything exponential. And so if I simulate this kind of model, I obtain usually one big epidemic at the beginning, and then some dump oscillations. That's in a deterministic model. And when I simulate the same thing with the stochastic models, well, I have many trajectories, and what I have here, for instance, it's recurrent epidemics, kind of, that at some point goes extinct. So that's, you see intuitively that the longer my disease will last in this population, we can maybe consider that this population is above the CCS. So I'm going to try to quantify these fade outs, how early, how late they occur in the populations when you are at endemic equilibrium, that after this transient phase. So that's the SIR model with birth and death, and we consider the expected time to extinction, so the expectation of T omega, as a measure of persistence. So the greater is T omega, the longer the disease persists in the population, and so that's the minimal time so that the number of infectious people is equal to 0. So at what time the number of people reach 0, infectious people reach 0. And as I said, this is something that we want to look at endemic equilibrium. So in a deterministic model, it's very simple. You simulate your model for a long period, and then you see some endemic equilibrium. In a stochastic model, we have something similar. Obviously, if you simulate for infinite duration, everything will go to extinction. I mean, there is only one. There is an absorbing state, so the chain will end up in this state at some point. So we're going to look at the quasi-stationary distribution, which is the distribution on the long term, but conditioning on non-extinction. And the fact is that this is well defined for this kind of model where you have a constant population size and only a finite set of absorbing states. What we know as results is that for this kind of models, the expectation, the time of the persistence time follow an exponential distribution. And so you see here 1 over the sum of the death and recovery rate, correspond to the rate at which you exit the infectious compartment, multiplied by the value of this quasi-stationary distribution when you have only one infectious guy in the population. So that's the probability to exit this state where you have only one infectious individual And so it's the marginal probability of having a single infectious individuals at quasi-stationarity. And the idea is that obviously this is difficult to compute analytically because we don't have results for this. So one possibility is that because I'm going to consider quite big population size, I'm going to consider like 10 individuals, maybe I can use the Gaussian approximation to kind of estimate this probability here. That should be quite small. So that's not obvious at all, but that's what has been proposed. And when you do like some numerical comparison between the analytical results and some Monte Carlo simulations, it's in good agreement. So you put yourself in the position where this kind of approximation is going to be more or less valid, and that's why you obtain this where you obtain your results analytically. So that's an heuristic. Use the endemic equilibrium of the Gaussian approximation to approximate the quasi-distribution. Okay. So now so that's just the tools we're going to use. And now how we define like properly like the CCS. Well, Bartlett in the 60s, he was interested in this. He made the plot I showed you before. He said that this is the size of the community for which measles is as likely as not to fade out after a major epidemic. So that's a definition. It's quite easy to see empirically how it's going to look like, but mathematically it's not precise enough. So Ingmar Nassel in 2005 he proposed the following definition. He said that the critical community size, so the CCS, is that value of omega, the population size, for which the median time to extinction equals 1 quasi-period T0. So it means that obviously if the median time to extinction is equal to the quasi-period, it's likely that my epidemic will go extinct before the next epidemic. And so because this is exponentially distributed, well, the median is T0 is equal to log 2 times the expectation. No, sorry, that's the quasi-period, and that's the median. And so you want these two things to be equal. And so the quasi-period is something that you can actually measure with the SIR model. I think probably Seb, you talked about it in the SIR model, the quasi-period. But given the parameter of measles, so R0 around 14, for instance, an average infectious period of 1 week and 70 years of duration of life, you have a quasi-period of around 2 years, so an epidemic every 2 years in average. And so if you use the Gaussian approximation to compute this value, because you need the distribution, the quasi-stationary distribution, then you replace, and when you obtain is that the omega CCS that solve this is equal to 115,000 individuals, which is kind of in good agreement with what you see here. So it's a very simple model, but it gives you like the right order of magnitude for the CCS, which kind of confirm that probably like demographic stochasticity is a very important mechanisms of this kind of like extinction during the endemic dynamic. I have a few more examples. I don't know if I have time. What time is it? I have still 20 minutes? Yeah? Unless you want to do a break. I can finish maybe a bit quicker. So the third example is to look at the dynamic of measles and pertussis, so whooping cough, in London before and after vaccination. So here you have measles outbreak. So you see, like I said before, like the entire epidemic period is around 2 years. Huh? Here, every 2 years you have an outbreak. And then at some point they introduce the vaccine. And what you can see is that it has a very huge impact on the dynamic of measles because the amplitude of the epidemic decrease. But also you see that the frequency of the epidemics seems to be much less, much more variable than before, where you have like very regular outbreak. Now here it's more, it seems to be more happening like very different time, not very regular. Sorry. For pertussis, it's kind of the opposite. Before vaccination, you have these epidemics that are not very regular, and also the amplitude, well, many are not very regular. And after vaccination, you see that the epidemics are more regular, but also that the amplitude is not that much different from before. In comparison to what you see for measles, here you have like the amplitude seems to be kind of the same order of magnitude as before. So that's two amazing graphs. I mean, there is not a lot of field where you have like a time series that span over like 50 years. And obviously, like a lot of mathematical biologists, they were very interested in these patterns, trying to understand what could be the mechanisms underlying these different patterns, and why, when you consider measles and pertussis, which are very similar, both childhood diseases, with kind of similar parameters, why is that different? So, as I said, the biannual cycle of measles become irregular after vaccination. The multi-annual cycle of pertussis becomes more regular. And also both incidence decrease. The amplitude of pertussis epidemics is similar to that in the pre-vaccine era. So the question is how pathogens with similar or not, and infectious periods, between 1 and 3 weeks, can have such different dynamics and transitions following vaccination. And so there were two paradigms to explain this switch, this change. The first one was a deterministic paradigm, is that you have complex interaction between nonlinearity due to the mass action, the contact process, and seasonal forcing that correspond to school closure, for instance, and reopening. So you have like some complex interaction between these two mechanisms that create amplified oscillations, that what we call resonance, and a very rich dynamics. And in these paradigms, stochasticity just play an external role. It's just gonna, imagine you have like two attractors in your model, and the stochasticity is just gonna make your system switching from one attractor to another, and that's why you might create very rich dynamics that potentially explain the change in the dynamics before and after vaccination. The stochastic paradigm is a bit different. It says that resonance depends on the capacity of demographic stochasticity to amplify oscillations. It's a bit like in a bridge. When you work on the bridge and you have some oscillations, that can be amplified depending on the frequency of which frequency you work on the bridge. And so this is an active role of stochasticity in this case. And so some people, in the 2007, Alonso and colleagues, they look at the Gaussian approximation to derive some quantities regarding the stochastic process. First one is amplifications, so the system capacity to sustain and amplify the stochastic fluctuations. And coherence, which measure the concentration of spectral power around the dominant endogenous frequency. So coherence is how regular will be your epidemic, and amplification is how high they will be. And so they use the SIR model I showed you before with birth and death, and then they have this phase plot, where here you have the reproduction number, beta over gamma, and this is the ratio of the infectious period over the duration of over the life duration, sorry. And you see that this is the amplification is higher here and lower here in blue. And then they mapped like different childhood disease. And for instance, this is the pertussis. and this is measles. And you see that they simulated the effect of vaccination by decreasing R0. So it's roughly like, you can see that when you vaccinate, you have a greater proportion of immune people. So that's going to decrease the effective reproduction number. And at endogenic equilibrium is a bit the same as decreasing the reproduction number. So that's why they show here. So that pertussis, when you decrease, so when you vaccinate, you see that actually you stay in kind of the same area for amplification. Where for pertussis, you're gonna increase the amplification. So you're gonna be so yeah, for pertussis you have more amplifications. That means that given an outbreak, you might have like bigger peak just because you're gonna amplify the peak. And so that's why for pertussis you have this kind of like, I mean, they would explain this by an amplification of the oscillations. Where here, where you can see the effect of the vaccine, and there is no amplification especially, so you won't expect to see something increasing. The second thing is coherence, because here you see that less regular, more regular. So the same thing, the coherence, well, for measles, the coherence decrease, whereas for pertussis, the coherence increase. So you expect to see more regular epidemics for measles. And that's what you can see on the plots. So that's really like, obviously it's quite qualitative, it's not like fully quantitative, but it can tell you that demographic stochasticity, there is a lot of rich dynamics, and there are some phenomena like amplification and coherence that can be very different depending on which disease you consider and which part of the parameter space you are. And so that was for this example. And just to finish with the last example, I'm going to consider a two-wave flu outbreak on the island of Tristan da Cunha. So that's an example I've been working on during my PhD. And the interest here is that it's a very small population, so you might want to use a stochastic approach just because you may expect that there is a lot of random events that may have a big influence because it's a very small population. So it's a simple outbreak, but a small population. So Tristan da Cunha is the most isolated inhabited place in the world. We probably never heard about it, but it's located here. And it's a volcanic island which has only one village that where like around like 300 individuals has been living there for a long time. It's fully isolated, and there is no much contact with outside. And what we call free social mixing means that people share most of the places in this village, the canteen, the church. So there is no particular like social structure in the population. And it's so isolated that actually this island escaped the deadly Spanish flu. It's one of the only places that escaped the 1918 Spanish flu. And this is because it's 1 week of travel of boat from Cape Town. And so you can see that because flu, the generation time is really short, usually the outbreak die on the boat before reaching the island. But in 1971, bad luck, there is a boat that returned from Cape Town, and a few individuals have been infected during the journey. And 2 individuals land on the island with flu symptoms. And at this point, they have a tradition to have some dancing. And so everyone mixed, and the result is quite dramatic, because in a few weeks, in only like 2 weeks, 96% of the 284 islanders were developed disease, flu symptoms, and you have this huge peak of influenza. So that represents 96% of the population. That's a lot. And that's because the population is very naive to influenza. But as the epidemic was dying out after 2 weeks, actually some people start to feel again disease. And they experience a second episode of illness. And that triggers a second wave of the epidemic, where 32% of the islanders were reinfected during the second wave. The thing is that this data set was mostly unexplained. There was some empirical evidence that it was influenza H3N2 that was circulating. At the time, there were evidence that some people got twice the infection, but it was not clear why they were infected twice, and that's very uncommon to see that for flu. So, yeah, lack of empirical data to explain this two-wave epidemic. And also, there is some underreporting, because we know that in the data set, there is only 85% of the 365 episodes of illness that are known. So the objective of the work here was to use mathematical modeling to disentangle between 5 biological hypotheses that could explain these cases of rapid reinfection. And we want, because it's a small island with a few inhabitants, we want to take into account demographic stochasticity, the dynamic, and also in the reporting, in the observation. So here, we're going to have like the two sources of stochasticity, observation and demographic. So I'm going to go through the the 5 hypotheses, and that will show you also some example of more complicated models than just SIR. The idea here is that we're not interested into analytical results. We just want to have a model that kind of match with the biological assumptions. And we want to have like minimal model. That means that it's complex enough to describe uniquely an hypothesis, but simple enough to be able to be fitted to the data. So earlier I showed you a graph similar to that, where you have the exposed, infectious, and immune response. But actually, it's a bit more complicated for flu, because you have 2 types of immune response. The first one is the innate and cellular response, which is going to repress the viral load. But usually it takes some time before you develop a long-term immunity, which is antibody-mediated. And so we're going to consider a temporary immunity, that is until the completion of the cellular response, and long-term immunity, which corresponds to when the antibody reaches a level high enough to be protective. So that's what we call SEICH, cellular humoral response. And obviously here, so that describes the primary immune response to influenza when you first meet a new flu virus. And so there are some parameters, classic. And here, obviously, you can only have one infection. There is no reinfection. So now I'm going to go through the 5 hypotheses, how to simulate reinfection based on this model. So the first idea is that the mute model is that the virus mutated during the first wave of the epidemic. So at some point, I just put one guy here, and I put it here. And once in this mutated compartment, well, it can reinfect people, both susceptible, but also people that were immune with the first virus at a given rate. And so when they are reinfected, they become exposed, infectious, and again, cellular and humoral response to this new virus. And this infectious rate is multiplied by a scaling factor, or sigma, which corresponds to the cross-immunity between these 2 viruses. So the second hypothesis is that there were 2 viruses. It's a very similar structure, except that here I have different force of infection. So the idea is that since the beginning there were 2 different viruses, one probably with a high R0 and one with a small R0. And so the first one spread quickly and the second one more slowly. And so you can retrieve this kind of 2 waves outbreaks with these models. The third model corresponds to only one virus, but some intra-host reinfection. So some people, after recovering, they didn't fully repress the viral load, and so they were able to be reinfected with probability 1 minus alpha. Otherwise, they would have developed a full protection. So here you have intra-host reinfection. The fourth hypothesis is the hypothesis of partially protective immunity, which means that everyone develops a long-term protection, but it's only partially protective against reinfection, so you can still be reinfected at a rate, at a decrease, a smaller rate that corresponds to the partial immune protection. So if you have a fully protective immunity, this would be 0, and at the opposite, if sigma is equal to 1, that means that you have no partial protection. You want something in the middle, obviously. And the last hypothesis is a bit more complicated. Well, not so actually. The idea is that you have some host heterogeneity. Not everyone responds the same way to a flu infection. Some people will have like a good cellular response, but a very weak humoral response. So in this case, they will have no humoral response, for instance. So after the cellular phase, they become susceptible again. Or some people will have a delayed long-term immunity. So the long-term immunity will arrive, but with some delay. And so you have some potential here between these two immune response of a window of reinfection, opportunity that if you are exposed again to the virus, you become infected again. And so this is how it is modeled. We create a new compartment here between C and H. And you see that when you are here, you can be reinfected at the same rate as susceptible people. Okay, so that's the 5 model. And I'm going to skip this. It's just to show you how you match data with models. And when your model is stochastic, actually you cannot write the likelihood, which kind of link the data to the model. And so that's why you need to use Monte Carlo approaches. So in the inference, you are interested in estimating the parameters. And so for each parameters here, each box is a parameter. So for some parameters that are shared by different models. So for instance, every model has a R0, but only these 2 models have a probability of long-term immunity alpha. So you have different estimates for different models. But what you want to do also when you confront models to data is to try to compare models between themselves. And for that, you're going to use, for instance, based on the maximum likelihood, you're going to look at what is the maximum likelihood of each model and what is the number of parameters of each model. And you're going to combine these 2 things into what we call the AKIK information criterion, which penalizes for model complexity. And then you can compare the different models. So here you have the different models, and here the difference in the IIC. And you see that the best model is the one model, and then you have the different model here with kind of substantial difference in terms of the IIC, above 4. So when you see such difference, usually you accept this model and reject the other. So just by using the information in the time series and comparing stochastic models, you are able to say that this one better explains the data. I'm going to skip this just to show you why it's important to use a stochastic model here. Is when you resimulate all the models under the best fit parameter set. So here, for instance, I just take the mutation and the best model. I simulate a lot of trajectories. So you see that you can reproduce the 2 ways here, where here you can also reproduce 2 ways, but obviously a lot of trajectories went extinct here. And that is why it is measured by the extinction probability over time. So here at this time, because you have very low incidence, you have a big chance of extinction. And actually, this is because when you have a mutation, you introduce a new variant, and you have a risk of initial extinction. And this risk is quite high. In the best model, you see that the risk of extinction, despite the very low incidence, is almost 0. Just increase at the end. So if we compare all the models in terms of this extinction probability, we kind of understand why the best model is the best model, because it's the one who has a low extinction probability between the two waves, so it's more likely to create a second wave epidemic in comparison to all these other ones. But at the same time, the extinction probability increases at the end of the second wave, which means that you don't have a third wave. So it kind of tells you that this model is in good agreement with the data, and it's only with a stochastic model that you can separate all these. I mean, in this dynamic setting, all the model won't be able to measure that. Okay, so just to conclude, I hope that this talk will show you that the propagation of pathogens in a population is a process that is inherently stochastic, and the same as most of actually in-house dynamics or immunological problems. We are dealing with molecules, we are dealing with individuals, so that's discrete entities, so you might need to take into account stochastic effects. The problem is that it's difficult to have identical results, so you need to simulate using Monte Carlo simulations, and that's become computationally very intensive as the population size increases. So in some kind of situation we have large populations, it is very relevant and good to use deterministic approximations. And if you want to be something intermediate between fully stochastic and deterministic, you can use second order approximations, which lead to approximate the stochastic process by a Gaussian process. When you want to do fitting, there is no closed form for the likelihood. That's what I skipped earlier. So you also need to use Monte Carlo approach. All these things are computationally intensive. But one thing that we can notice is that with increasing computer resources, there is more and more stochastic modeling and stochastic fitting to data. And that's really like there is a move from deterministic towards stochastic approach in the field of epidemiology. And that's mostly due to the increase of computational resource and also to influence of many works. So yeah, thank you for listening. I almost finished on time. And well, if you have any question, maybe now or later, I don't know what is the program. Has anyone used a stochastic model already? I know one person.
Take a break now.
Yeah.